Hi, I'm Charles, and welcome to part 23 of the OpenSCAD video series. In this part, we're going to be talking about surface hulls with spherical coordinates. Let's get started. So, to do a surface hull on spherical coordinates, the first thing we need to talk about are spherical coordinates. So, I've got this little demo set up here. And I'm not going to go into the code of the demo, really. I'm more just interested in explaining the basics of how a spherical coordinate system works. So if we look here, we've got a point, and there's a line from the origin to this point, and this is essentially the radius of this sphere that you see here, and that radius is called rho, which in Greek looks like a P, but we call it rho. So this line right here has length rho, and essentially we use two angles to describe the position of this point in space. So we have phi, which is this one, which is currently 45 degrees, and phi is the angle of rho from rho to the vertical axis. The positive side of the vertical axis. So rho is 45 degrees, so you can see that rho is 45 degrees from the vertical z-axis, and designated by this angle here. The next one we have is theta, which is this angle here. And so if we take a bird's eye view, we can see this is the x-axis and this is the y-axis, and theta, as it usually is the angle around the z-axis. So we rotate counterclockwise like that, and so we can see that theta is about, well, it's exactly 45 degrees right now. So that's the angle. So essentially we have rho, phi, and theta, and this describes our position in 3D space. Now, we're going to get into this a little bit later, but rho doesn't have to be constant necessarily. It can be based on phi and theta. So let's go ahead with that, and we're going to start coding. Actually, before I start coding, let me demo what this does. So I can change theta. Let me change theta to 60. As you can see, it increased in the counterclockwise direction. You can increase it to 70. And now I will put it to run as an animation. Essentially, it's gonna run counterclockwise around the z-axis. Yep, and so that's essentially what happens. And we can when you see it going around, it's always staying on the sphere. We can also change phi. Change phi to 70 degrees. And so I think hopefully you kind of get the idea of how a spherical coordinate system might work. You have two angles and a radius. So let's get started with the coding. So the first thing that we're going to want to do, just as an example, we're going to use cubes because they're simple shapes. We'll say the size equals 0.5, center is true. And right now we'll let rho be constant. We'll say rho is, say it's 10 units. So we translate rho units up in the z-axis, and as we can see, we have our cube up here that's been translated up. Next, we want to rotate it by phi. So phi is going to be a rotation around the y-axis. So the reason it's going to be a rotation around the y-axis, which is this axis here, is because it's going to move it over here to the xz plane. It's going to stay in the xz plane. If we rotate it in any other axis, well, z, it wouldn't do anything, and in x, it would move out of the xz axis. So we want it to stay in the xz axis on the positive side of x, so that when we rotate it, we know it's being rotated by phi after we, no, not by phi, by theta after we've rotated by phi. It's probably easier just to show. So here, the y coordinate, and we will say theta, and we haven't defined theta yet, so we'll say theta equals 45. Whoops. Okay, there we go. We can clearly see it's come 45 angles down from the vertical, 45 degrees down from the vertical. Okay, so next we have the phi component, and then we have the rho component, and now we want, sorry, this is supposed to be phi. And hopefully that wasn't too confusing. This is supposed to be phi. Does the same thing, but they're just different angles. So now we define theta. We'll say theta equals 30 degrees, and we'll add another rotate statement. And this is around the z-axis, theta. There we go. So as we can see, we could move it from there times time, and we can see the same thing that was happening more or less in the animation before in the demo is happening here. We just have cube moving around. We can change phi 70. If we want it to be on the xy plane, we can change it to 90, and now it's flat on the xy plane. Okay, hopefully that makes some sense. So now we have the basis for our function, or our surface hump. So let's get started on that. We know we need 2 for loops. So the syntax for that, we're going to start with I, j, so we'll say 0, and we haven't defined these variables yet, but we will. Step 1 through to 2, 0 through step 2 through to 2. So we'll say step 1 equals 0.1, step 2 equals 0.2, and 2 equals 1. Okay, so now we have our for loop to generate our points and move our shapes, so that's good. So we're going to create some new variables. We're going to move rho outside for now. And that creates something for us, but it is not at all what we need. So phi and theta are going to become dependent on I and j. So phi, we want phi to go from 0 to 180 degrees, because that's the limit of it. It goes from the top here, wraps around, and all the way to the bottom. So 180 degrees. So it's going to be 180 times I, because I goes from 0 to 1. And so that's going to take it from 0 to 180. And we're going to need a second variable called Phi2. And we want I plus step 1. Okay, now theta is 360 degrees, so we want to multiply by 360 times j for theta, and we need a theta 2 as well. Whoops, I didn't add the 2 to the phi. And j plus step 2. Okay, and now we kind of see what might be happening. Kind of looks, well, from the top it looks a little bit like a star. That's not exactly what we want, but it's a good start. Here, let me change this back to 0.1, which is what I wanted originally. Okay, so this kind of looks like a ball now, which is a good thing. It means we're getting to the right place. So, okay, so now we have our 4 points. If you watched the last video on surface hulls, this will make more sense. But so essentially we need four points. So we're going to start with our first triangle. So we have our first point, and something else that we're going to define is the size of the cubes, because we're going to need to, there's a lot of copy and pasting, so it's probably best just to set it at a certain point. So we're going to say s is equal to 0.5, so we'll leave it the same, and we'll just say s. Another thing we're going to quickly change before we go any further is rho. So remember I said rho can be a function. We're going to change it to potentially be a function, but for now we'll just have it return 10, but we'll have it take arguments just so that the copying and pasting is a little bit easier. It's terrible coding practice to use copying and pasting, and you want to avoid it as much as possible. But here you kind of have to. It's really hard to get around. Okay, and yeah, really hard to get around and still be efficient. Okay, so now that we've changed that, we'll say rho phi theta. Okay, so P and T for phi and theta. And just clean up a little. And it does exactly the same thing, which is what we want. We haven't made any changes that we want to be able to see yet. So we want to start with our first triangle. So we need 2 more points for the triangle. And as we know, we need these 2 to be the original. We need to change one here, and we need to change one here. So let's start by changing theta. We'll say theta 2. And theta 2, whoops, I forgot to make that pretty. And now in this one, we will make it phi 2. Phi 2, okay. So we'll save, and again, it shouldn't look like anything's changed, but something actually has changed. We have more points now. So what we can do is now hull these all together. And we should see some triangles with gaps in them. Perfect. That's exactly what we wanted. So we've made the upper triangle. And now we need to make the lower triangle. So essentially what we can do is copy and paste this whole thing It's exactly the same, except we're going to change the first point. Let me just comment this. Upper triangle. Lower triangle. Okay, and we want, in our first point, we want them to both be 2. So theta 2 and phi 2. Hopefully that loads. Yes, that's really quick. Now you might be wondering, why on earth would we do this? It seems like you can only make a sphere with this, which would essentially be useless. And that would be correct, because we don't want to just make a sphere with it. So the fact that rho can be a function is really useful for us. And we're going to look at that now. So we can quickly we can change this to be smaller so that it looks a little bit better. It looks more like whatever shape we're going for. And the reason I'm leaving the steps so coarse is that it will start to take time to load if I make them any finer. So for at least a little bit, maybe for the final render, I'll increase it, or final preview, I'll increase the steps. But for now, I'm going to leave it fairly coarse, just to illustrate the point. Okay, so we'll say 10 plus 4 times, so P stands for phi and T stands for theta. I'm going to move this over so we can see the whole function. Actually, I'll just take it under so that there's more space. Sine of phi times sine of theta. And maybe 2 times and 3 times. And that gives a really interesting shape. That's just one of the possible shapes that you could do. Maybe I'll make this slightly more fine, just so you can get a better idea of what it's actually like. There. And so that's a really interesting shape, in my opinion. That it's really hard to get with other methods, and spherical coordinates. Yeah, a spherical coordinate system makes it much easier. Okay, but there's a problem. If you notice that you look inside, it is hollow. Maybe if it's not clear, I will reduce this value. And it's hollow inside. So you might be wondering, how do I fix it being hollow? So there's actually a really quick fix for the hollow issue. It doesn't work. It wouldn't necessarily work in all circumstances, but it would most likely work in a lot of circumstances. So you just copy and paste the cube. Right there. Maybe be able to see what it does. It fills it in. It essentially fills the triangles into the origin. Let me see. I will make this transparent so we can kind of see that the upper triangles are now connected to the origin. And we'll just add another one to the lower triangle. And now you have what appears to be a solid shape. So I will change it back from transparent, and there we go. Not bad. we might have to subtract a little bit. If we just subtract the step, it will there we go. Because it was just going a little bit further than it was supposed to. But now it's fine. Okay, cool. Let's change this back to 1 and this back to 0.1. There we go. And now we have a solid shape, which is good. It might be what you want. It also might not be what you want. You should be able to, if you don't necessarily want it to be solid like that. Here, let me make this a bit bigger. There we go. Change this back to 0.5. Not necessarily solid. So what we can do is translate this. And by essentially the same amount, how do I put this? The same amount as before. Actually, we can just get rid of this altogether. And we would have to, oops. Copy these 3 points. And we can subtract 5. So it's going to put them a little bit not as far out as they're supposed to be, so that it just adds thickness as opposed to making it really solid. So let me get rid of this one just so we can see what's going on. There we go. We can kind of see they look like compartments. We can see that the upper triangles are solid, but we still have gaps. That's just because we haven't done the lower triangle. So we can do the lower triangle. Hope I'm not rambling too much. This is making sense. And this is a little bit speed done, so it's not the best. But these could be given a variable, and that would yeah. So that essentially gives it a wall thickness almost. So let me quickly change that number to thickness equals 5. And this is why you use variables and why you don't copy and paste code, because it then takes forever to modify. Okay, it's the same thing, but now we can change this. Let's see, we wanted a thickness of 2. Yeah, not bad. Okay, and we can increase this a little bit, hopefully. Yeah, there we go. Oh, and maybe this one too. Nope, I'll change that back, but we'll get a nicer version. So that's kind of pretty looking. So yeah, that's mostly I think that's mostly it for surface hulls and spherical coordinates. It's a fairly straightforward process. You essentially translate your cube up and you rotate it in the XZ plane, then you rotate it around the Z axis, and you use the upper and lower triangle method to create a hulled surface, and you can double up and essentially create a thicker object instead of a really thin object. And you can barely, well, you can see them, but you could essentially make the cube so small that you can't see them. So when you look at them now, they're really difficult to see, and they just look like points. But when you do that, if you just had a shell, it would be really hard to, well, you just wouldn't have any thickness. So with this method, you add thickness. Now, I haven't tried to 3D print any of these, so I don't know if it causes some problems, like non-manifold edges. Hopefully not. Maybe someone can let me know. But otherwise, that is mostly it. So I'm going to render it nicely now. The full shape, hopefully it shouldn't crash. That's another thing to note, that OpenSCAD, especially when doing double for loops, can be really messy. So these parameters are quite limited, and if you make them too low and you make it so that there's too many steps, the program will just crash. And I think there's an upper limit, and I'm not sure how to change it on how many points can be rendered. So yeah, let's just render that. And there's an alternate way of doing this by calculating the X, Y, and Z position of the point, but I thought it would just be simpler to I thought it would just be simpler to use the rotate and the built-in methods. Okay, so we need to add back these steps. It's a little strange, but there we go. All fixed, all better. Yep, and you have a really interesting shape. I mean, you can play with this to no end. Like, you could use the cosine function, for example, and you can change the internal parameters. You can multiply by t and p in the same function. You could have lots of fun with these functions. I wasn't quite sure of the names of these functions, so I couldn't really find examples on the internet, but I'm sure there's plenty somewhere. Okay, that's it for now. So thank you for watching, and hopefully I'll see you in the next one.